A lost city reveals itself not to a shovel, but to a satellite. Archaeology is in the midst of a revolution, one where we decode history by light. We are now using satellite spectral imaging to peel back the layers of time, uncovering secrets hidden for thousands of years. By the end of this, you will understand how light has become our most powerful time machine, capable of finding entire civilizations without moving a single grain of earth. How many ancient empires are still waiting beneath our feet, completely invisible to our eyes? What forgotten story would you most want the light to reveal for centuries? The archaeologist's most trusted tool was the trowel, patiently scraping away time, one thin layer at a time. This meticulous work built the foundation of our understanding, but it was like reading a history book by looking at a single letter on one page. You had to know exactly where to dig, and the process itself could inadvertently erase the very clues it sought to find. The breakthrough came from a simple but profound insight. Human settlement leaves a permanent scar on the land, a ghostly impression that lingers for millennia. When people build structures, farm the soil, or even just walk the same paths for generations, they change the earth beneath them. They compact the soil, mix in different materials like plaster or organic waste, and dig ditches that fill with unique sediments. These activities create subtle differences in ground moisture, soil chemistry, and even the nutrients available to plants growing on the surface. From the ground, these differences are utterly invisible. But from space, seen through the sophisticated eyes of a satellite sensor, they paint a vivid picture. Each type of altered ground reflects light in a slightly different way, emitting a unique spectral fingerprint. It is the ultimate form of non-invasive detective work, allowing us to scan an entire jungle or a vast desert from orbit and pinpoint the exact location of a buried wall or an ancient road. This is not just a new tool, it is a completely new way of seeing. We are no longer limited to a single test pit. We can now read the entire landscape at once. Our eyes are incredible tools, but they are also profoundly limited. They perceive only a tiny fragment of the light that exists, a narrow band we call the visible spectrum. The full reality of light, known as the electromagnetic spectrum, is unimaginably vast. It stretches from the incredibly short wavelengths of gamma rays to the waves that can be miles long, used for radio transmission. What we see as colors is just a small island in this immense ocean of energy. This is where the true magic of satellite archaeology begins. Specialized sensors on satellites are built to see this entire spectrum. They capture information in wavelengths invisible to us, like infrared, which is essentially heat radiation, and microwaves. Every single substance on our planet interacts with this full spectrum of light in a unique way. A patch of soil, a block of limestone, a body of water, or a field of wheat, each one absorbs certain wavelengths and reflects others. This creates a distinct signature, a kind of optical fingerprint that is utterly unique to that material. A buried stone wall, for instance, will heat up and cool down at a different rate than the loose soil surrounding it. This creates a thermal fingerprint. Or the compacted earth of an ancient road might retain less moisture, affecting how it reflects infrared light. By training computers to recognize these subtle spectral fingerprints from space, scientists can literally map the ghosts of human activity. They can distinguish the signature of a buried irrigation canal from the natural clay around it, or spot the outline of a long-vanished building foundation beneath a farmer's field. This principle of spectral analysis is the master key, the fundamental breakthrough that allows us to read the landscape like a historical document. With this key in hand, we can now look at the specific technologies that turn this principle into a detailed map of the past. This technological arsenal operates on a simple but profound principle of differentiation. The most common tools in this new age of discovery are multispectral sensors. Think of these as having a set of 8 distinct crayons. Each crayon represents a broad band of light, like visible red, green, blue, and several types of infrared. By combining these bands, we can get a very good picture of the land, distinguishing forest from farmland or water from desert. It is a powerful overview, perfect for spotting large features like the outlines of buried forts or ancient river channels. But the true revolution, the leap that has turned archaeology upside down, comes from a far more advanced tool, hyperspectral imaging. If multispectral is a box of 8 crayons, then hyperspectral is a box containing every single shade imaginable, thousands of them. These sensors do not see in a few broad bands. They break reflected light into hundreds of incredibly narrow, contiguous slices across the spectrum. This creates an exquisitely detailed chemical portrait of the Earth's surface. This incredible resolution is what allows us to detect the faintest whispers of the past. Minute changes in soil chemistry left by human activity become glaringly obvious. A patch of ground rich in phosphates, a chemical signature of decomposed food waste and human habitation, reflects light in a unique way that a hyperspectral sensor can pinpoint. Similarly, minerals like limestone, which our ancestors used for building, leave a distinct spectral mark that differs from the surrounding native rock. These sensors are not just our eyes in the sky, they are our chemical analysts in orbit, discerning the ghostly impressions of a settlement's footprint long after its walls have crumbled to dust. But this raw torrent of data, this river of spectral information, is just the beginning. The real challenge lies in teaching a computer to see the patterns that our own eyes would forever miss. This river of raw data is more like a chaotic symphony than a simple picture. Each pixel in a satellite image holds a numerical value, a precise measurement of how much light is reflected in hundreds of different wavelengths. To the untrained eye, it is an indecipherable spreadsheet of numbers. The first and most crucial task is to clear the static. Our atmosphere is filled with water vapor, dust, and other tiny particles that scatter and absorb light, distorting the true signal from the ground. Scientists perform a process called atmospheric correction, which is like carefully cleaning a dusty window pane. They strip away this atmospheric noise to reveal the pure spectral signature of the soil, the stone, and the vegetation below. Only then can the real analysis begin. The next step is to teach a computer to recognize patterns in this clean data. Sophisticated algorithms scan the landscape pixel by pixel, comparing each unique spectral fingerprint against vast digital libraries. These libraries contain the known light signatures of thousands of materials, from specific types of clay to particular minerals. But with hundreds of data points for every single pixel, the complexity is staggering. This is where a brilliant statistical technique comes into play, known as principal component analysis. Think of it as a master editor for an overwhelmingly detailed story. It identifies the most important themes, the most significant variations in the data, and simplifies everything else. It highlights the subtle differences that truly matter, like the spectral shift between natural soil and soil that was once the floor of a human dwelling. The final step is where science meets art, visualization. These subtle, mathematically derived differences are invisible to our eyes, so researchers assign colors to them. They might paint the signature of buried limestone a bright red and the surrounding soil a dull blue. Suddenly, what was a spreadsheet of numbers transforms into a vivid, intelligible map. The ghost of a structure emerges, a geometric pattern of red against a field of blue. This entire meticulous process, from cleaning the data to painting the picture, turns abstract numerical values into a powerful archaeological guide. But a map is only a theory until someone walks the ground to see if it is real. The legendary city of Ubar seemed destined to remain a story. For centuries, its existence was debated, a fabled metropolis of immense wealth mentioned in ancient texts like the Quran, said to have been swallowed by the desert as punishment for its arrogance. Explorers searched the vast, empty deserts of Oman for generations, finding nothing but sand and sun. The traditional tools of archaeology were almost useless in a landscape so vast and unforgiving. The challenge was not just finding a needle in a haystack, but finding a needle in a haystack that had been buried under another haystack. The turning point arrived not with a new expedition, but with a new perspective from orbit. A team of researchers led by archaeologist Joris Zarins turned to satellite spectral imaging. They used a specific type of data, radar, which has the unique ability to penetrate extremely dry surfaces like desert sand. From this incredible vantage point, they began to see what no one on the ground ever could. Faint, ancient pathways emerged from the data. These were the fossilized tracks of countless camel caravans, worn into the earth over centuries and then hidden by relentless dunes. On the satellite maps, these tracks did not wander aimlessly. They converged like the spokes of a giant wheel, all leading to one central point in the middle of the Shisha Desert. That point also showed distinct spectral anomalies, telltale signs of something man-made hidden just beneath the surface. The data was so compelling that it guided a ground team directly to the spot. Their excavation revealed the massive, octagonal walls of a fortified city, along with towers and artifacts, all buried for over 1,000 years. The mythical Atlantis of the sands had been found. Ubar was not a myth after all. It was a real, thriving trade hub, and its discovery was a landmark moment that proved spectral imaging could solve the greatest historical mysteries. It demonstrated that we could now follow ancient footprints in the sand, even when the sand itself had erased them from view. This single discovery opened the floodgates, showing that the light from space could illuminate histories far older and more mysterious than anyone had dared to hope. The ground remembers what we have forgotten, and sometimes it whispers its secrets through the very plants that grow upon it. This is the principle of the Vegetation Index, a concept that transforms entire landscapes into living, breathing historical documents. At its heart is a simple, powerful idea. When ancient builders dug a ditch or laid a stone foundation, they permanently altered the ground. A buried stone wall, for instance, creates a zone of shallow, dry soil directly above it. The plants trying to grow struggle, their roots unable to find deep moisture or nutrients. In contrast, an old pit filled with rich, organic waste or a buried irrigation ditch creates a deep, moist, fertile pocket. The vegetation there flourishes, growing taller, greener, and healthier than its neighbors. From our perspective on the surface, these differences are usually invisible. A field of wheat looks like a uniform sea of green, but from space, seen through the right spectral eyes, the hidden patterns scream for attention. Scientists use a specific measurement called the Normalized Difference Vegetation Index. While that sounds complex, it is simply a way to precisely quantify plant health by comparing how much red and near-infrared light the plants reflect. Healthy, chlorophyll-rich leaves strongly reflect infrared light and absorb red light. Stressed or sparse vegetation does the opposite. By calculating this index for every single pixel in a satellite image, researchers can create a detailed map of plant vigor. Suddenly, a faint geometric line of stressed crops materializes, tracing the precise outline of a Roman villa's foundation hidden just a foot below the surface. A lush, dark green circle might reveal the location of a filled-in grain storage pit. These are the spectral crop marks that have revolutionized landscape archaeology. They allow us to see not just a single site, but the entire context of an ancient settlement, its property boundaries, its road systems, and its agricultural patterns, all written in the language of light reflected by leaves. This method reads the landscape as a palimpsest, an ancient parchment that was scraped clean and reused, but where the old writing still shows through. The spectral sensor is the one tool that can read that faded, underlying text without ever damaging the surface. Yet, for all its power to reveal structures, the real magic happens when this technology is trained on something far more ephemeral, the ghostly traces of landscapes that vanished millennia ago. The Roman Empire did not simply exist on the land, it engineered the land itself. Its vast network of roads, forts, and farms was the circulatory system of a continent-spanning state, and its ghostly imprint is still there, etched into the soil of Europe and North Africa. For generations, we have known about the major highways, the famous routes like the Appian Way. But spectral imaging is now revealing the empire's true scale, mapping its infrastructure on a level that would have been unimaginable just a few decades ago. The key lies in the unique materials the Romans used. Their concrete and road gravel have a specific mineral composition, a distinct spectral fingerprint that satellites can detect. When these mineral signatures appear in long, straight lines across the countryside, often correlated with faint lines of stressed vegetation growing in the shallow soil above them, the conclusion is inescapable. We are looking at a lost Roman road. In Tunisia, thermal infrared sensors uncovered something even more remarkable. A modern field appeared completely uniform to the naked eye. But from space, as the land cooled after sunset, a detailed blueprint emerged. The buried stone foundations of a vast Roman farm villa retained the sun's heat longer than the loose soil around them, causing a ghostly outline of the entire complex to glow in the thermal data. This was not just a small homestead, it was a major agricultural hub, a piece of a massive economic machine that had been completely erased from history. Each of these discoveries is a data point that is fundamentally rewriting our understanding of the empire. We are learning that Roman control and economic integration extended further into remote regions than any historian had proof of before. The empire was more extensive, more organized, and its footprint on the earth far more permanent than we ever knew. We are literally watching the ghost of Rome resurrect itself from orbit, line by line and road by road. This ability to see the grand patterns of an entire civilization raises a profound question. Can we use this same light to find what came before the empires, to uncover the very origins of human society itself? Stone and earth hold onto the memory of heat in profoundly different ways. A solid stone foundation, buried for centuries, possesses a property called high thermal inertia. This simply means it resists changing temperature. Over the course of a day, the sun beats down and the loose, dry soil in a field heats up quickly. But that buried stone wall heats up slowly, absorbing the energy. Then, when night falls and the temperature plummets, the loose soil cools down rapidly. The stone, however, releases its stored heat at a much more leisurely pace, remaining noticeably warmer for hours. This creates a hidden thermal landscape, an invisible map of temperatures that perfectly outlines what lies beneath. The key to reading this map is timing. The most revealing moment is often at the crack of dawn, just before sunrise. At that time, the loose soil has had the entire night to grow cold, but the buried stones are still gently radiating their leftover warmth. A thermal infrared sensor on a satellite passing over at that precise moment can detect this subtle difference. On the resulting data map, the ghost of a building will appear as a warm, geometric shape against a cool, dark background. The same principle works in reverse for features like ditches or pits. These depressions, long since filled in, often trap organic material and moisture. Water has a very high thermal inertia, so these damp areas also heat up and cool down slowly compared to the surrounding dry earth. A filled-in moat might appear as a distinct warm line in the early morning thermal data, clearly tracing the defensive boundaries of a forgotten fort. This method shines in open, arid landscapes where there is little vegetation or modern development to confuse the signal. In the deserts of the American Southwest or the plains of the Middle East, thermal imaging can reveal entire ancient village layouts with stunning clarity, as if the sun itself is etching the blueprints of the past onto the cool desert floor. The ground does not just remember what was built, it remembers the very energy of the sun that touched it, and it whispers that story to anyone who can listen in the right wavelength. This ability to feel the temperature of history from space is powerful, but it represents just one layer of a much deeper story. But what happens when the past is hidden not by sand or soil, but by an impenetrable green blanket? Dense jungle canopies have long been the ultimate shield, guarding ancient secrets from even the most determined explorers on the ground. A new kind of light has solved this problem, one that does not just look, but actively reaches down and touches the earth. This is LIDAR, or light detection and ranging. While it is a different technology from spectral imaging, it is the perfect partner in this archaeological revolution. Imagine a scanner mounted on a small plane or a drone flying over a vast, untouched rainforest. It does not take a photograph. Instead, it fires millions of tiny, invisible laser pulses at the ground every single second. Each pulse is a pinpoint of light that races down, hitting whatever lies below. Most of these pulses will be reflected back by the top layer of leaves and branches. But a lucky few will find a gap, a tiny window in the canopy, and continue their journey all the way to the forest floor. By measuring the exact nanosecond it takes for each pulse to make the round trip, the scanner can calculate the distance to the surface with astonishing precision. When you process the data from millions upon millions of these returning pulses, something magical happens. The computer can digitally filter out every single return that came from the vegetation. It simply erases the trees. What remains is a breathtakingly detailed, three-dimensional map of the bare earth, a topographic portrait of the ground that has been hidden for 1,000 years. This is not an artist's impression, it is a precise, measurable model of the actual landscape. The results have been nothing short of earth-shattering. In the jungles of Cambodia, archaeologists used LIDAR to scan the area around the famous temples of Angkor. They knew it was a significant site, but they had no idea of the true scale. When the digital trees were lifted away, the data revealed a sprawling, low-density urban network that stretched for hundreds of square miles. There were roadways, canals, village mounds, and intricate water management systems. This was not just a ceremonial center, it was the largest pre-industrial city on Earth, a metropolis that had been completely lost to the jungle and to history. A similar story unfolded in the dense rainforests of Central America. LIDAR surveys have exposed the true extent of Mayan civilization, revealing vast ceremonial centers, complex networks of elevated causeways connecting cities, and immense agricultural terraces carved into hillsides. We now know their societies were far more populous, interconnected, and advanced than we ever dreamed. LIDAR gives us the ultimate topographic canvas, the precise shape of the land, and every human-made feature upon it. Spectral imaging then adds the color, painting in the chemical and compositional details. Together, they form an unbeatable duo, allowing us to not only find a lost city, but to understand how its people lived, farmed, and shaped their world. Every single human settlement, from the smallest village to the greatest city, leaves behind a unique chemical ghost. Long after the last fire has died and the final walls have crumbled, the soil itself holds onto the memory of daily life. For generations, archaeologists have used this principle on a small scale, taking soil samples from test pits and analyzing them for chemical traces. The most famous of these is phosphate, a compound that skyrockets in areas of food consumption, animal pens, and human waste. A high phosphate level is a direct chemical whisper of a place where people lived, ate, and discarded their refuse. But this ground-truthing method is painstakingly slow, like trying to understand an entire library by testing the paper quality of a single page. Satellite spectral imaging changes the game completely. It allows us to perform this same chemical analysis from orbit, but across an entire landscape at once. Every mineral, every chemical compound, has its own unique spectral fingerprint in the infrared and beyond. The sensors are so sensitive they can detect the subtle spectral shifts caused by minerals introduced or altered by ancient industry. The chemical residue from a pottery workshop, where specific clays were processed and fired, creates a distinct signature. The limestone dust from a stone quarry, or the mineral byproducts from ancient metal smelting, all leave a permanent chemical stain on the Earth. By creating vast mineralogical maps, scientists can now see the entire economic engine of a lost society laid out before them. They can identify industrial zones, pinpoint the location of workshops, and even trace the trade routes of raw materials. You are no longer just looking at the outline of a city. You are seeing its economic heartbeat, its industrial districts, and the very chemistry of its daily life, all painted in light from hundreds of miles above. This chemical portrait connects us directly to the people themselves, to their work, their crafts, and their waste. It reveals not just where they lived, but how they lived. And when you combine this chemical map with the other spectral layers, you begin to build a digital resurrection of a world, a reconstruction so detailed it feels less like archaeology and more like a form of time travel. These ancient farms were the true engines of civilization. Long before the first stone of a pyramid was laid, a society's survival depended on its ability to feed itself. The most brilliant cities could not stand without a foundation of bread and grain, and now spectral imaging is uncovering the incredible agricultural landscapes that made empires possible. High in the Andes, around the shores of Lake Titicaca, the land seems barren and flat, but from space, multispectral sensors revealed a breathtaking sight. A vast geometric network of raised fields created by the Tiwanaku culture over 1,000 years ago emerged from the data. These were not simple gardens. They were complex, elevated planting platforms separated by water-filled canals. This ingenious system created its own microclimate, protecting crops from frost and using the water to absorb solar heat during the day, releasing it slowly at night. The canals also teemed with aquatic life, providing a sustainable source of fertilizer. This was a masterwork of ecological engineering, a breadbasket that sustained a powerful kingdom in a harsh, high-altitude environment. Meanwhile, in the deserts of the Middle East, another spectral story was waiting. The cradle of civilization, Mesopotamia, was built on irrigation. Its legendary city-states like Ur and Uruk transformed dry plains into fertile fields with an intricate web of canals. Over centuries, these canals silted up and vanished, leaving no trace for the human eye. yet their ghostly impressions remained, subtly altering the moisture and mineral content of the soil. Spectral imaging mapped these long-buried waterways with stunning clarity, showing how ancient engineers diverted water from the Tigris and Euphrates rivers to create an agricultural paradise. These discoveries are far more than just maps of old farms. They are blueprints for survival. They show us how societies solved the fundamental challenges of their environment. By studying the scale and sophistication of these systems, we can understand how a civilization like the Tiwanaku supported a dense population, or how the Sumerians managed their most precious resource, water. This knowledge holds a sobering mirror to our own time. The failure of these agricultural systems, whether from climate change, soil salinization, or political collapse, often spelled the end of the civilizations they supported. The light from space is showing us not only how these societies thrived, but also the precise reasons why they eventually fell. We are reading the last chapters of their history written in the soil of their abandoned fields. A single satellite image is a powerful snapshot, but the true story of a landscape unfolds across decades. The most profound power of this technology may lie not in a single moment, but in its ability to document the relentless passage of time. We now possess a continuous photographic archive of our planet stretching back over 40 years, thanks to missions like Landsat. This creates an unprecedented historical record, a time-lapse film of the Earth's surface on a grand scale. For archaeologists, this archive is a revolutionary tool for monitoring change. By comparing images from different years, they can perform what is known as change detection analysis. This process highlights even the subtlest alterations to the land. A faint geometric crop mark visible in a 1985 image might be completely plowed under by a new housing development in a 2010 photo. This is not just an academic exercise, it is a race against time. Looters, armed with their own simple satellite maps, often target remote sites. The scars of their illegal pits and tunnels are glaringly obvious in change detection analysis, allowing authorities to identify and protect vulnerable sites before they are completely erased. This same technique tracks the slow creep of urban sprawl, the shifting coastlines from sea level rise, and even the gradual drying of ancient riverbeds due to climate change. This temporal view also sharpens our vision of the deep past. By analyzing seasonal changes over a known archaeological site, scientists can identify the perfect window for discovery. A buried ditch might only reveal itself as a line of lush, green grass during a few parched weeks in late summer, when the deeper soil moisture gives its plants a vital advantage. A stone foundation might become thermally visible only during a brief period at dawn on a cold, clear morning in early spring. This fourth dimension, time, transforms a static map into a living narrative. It shows us not only the ghost of a lost city, but also the story of its slow disappearance, a chronicle of erosion, neglect, and modern pressures. This is archaeology in motion, a vital perspective that allows us to fight for the preservation of our shared heritage before the final traces are smoothed away forever. The hunt for legendary civilizations is no longer confined to dusty scrolls and explorers' tales. Spectral imaging is bringing the full weight of scientific evidence to the search for places once laughed off as pure fantasy. Take the lost city of Tartessos in southern Spain. For centuries, it was known only from fleeting mentions by Greek historians like Herodotus, who described a fabulously wealthy kingdom of metal traders beyond the Pillars of Hercules. Was it a real trading empire or just a traveler's tall tale? Researchers are now scanning the marshlands of the Guadalquivir River Delta with satellites, looking for the spectral ghosts of a society that vanished over 2,500 years ago. They are searching for the chemical signatures of ancient metalworking, and the geometric patterns of buried structures that could finally pin this mythical kingdom to the map. But the most profound rewriting of history is happening far from the Mediterranean, deep within the Amazon rainforest. The long-standing narrative was clear. The Amazon was a pristine wilderness, a so-called green desert that could only support small, nomadic tribes. It was considered impossible for complex societies to flourish there. Satellite data is systematically demolishing that idea. Across vast stretches of the basin, spectral analysis is revealing earthworks of staggering scale and complexity. These are not just small villages. The data shows altered soils known as terra preta, or Amazonian dark earths, which are incredibly fertile patches created intentionally by ancient people through charcoal and organic waste. More startling are the massive geometric patterns, huge circles, squares, and perfect lines etched into the earth that are completely invisible from the ground. These are the traces of large, settled settlements that some researchers now call garden cities. They were not simply living in the jungle, they were actively engineering it, creating a managed, productive landscape that could support populations numbering in the millions. The spectral fingerprints of their altered soils and the stark geometry of their land management are the only surviving witnesses. This evidence suggests the Amazon was not a virgin wilderness, but a cultivated, almost domesticated environment, home to advanced societies that shaped their world on a grand scale. The line between myth and history is not just blurring, it is being erased by the light from space, forcing us to reconsider the very definition of a pristine world and the lost chapters of the human story written beneath the canopy. A single type of data can reveal a ghost, but it takes a chorus of different voices to resurrect an entire world. This is the power of data fusion, the seventh and perhaps most transformative principle in the archaeological revolution. It is the practice of weaving together disparate threads of information into a single, coherent tapestry of the past. Think of it this way: a LIDAR scan gives you the precise shape of the land, a perfect three-dimensional model of every hill and hollow. A hyperspectral image paints that same landscape with the chemical colors of its soil and stone, and a hand-drawn map from the 18th century might hold a crucial clue: the local name of a field that translates to Old Fort. Individually, each of these datasets tells an incomplete story, but when you layer them on top of one another in a powerful computer, something magical happens. A linear ridge spotted in the LIDAR data, a potential ancient road, can be cross-checked against the hyperspectral map. If that same line shows a distinct mineral signature for crushed limestone or compacted gravel, the case for a human-built feature becomes overwhelming. This is the process of cross-verification, where one type of evidence confirms and enriches another. The synergy does not stop there. Researchers are now feeding these fused datasets into machine learning algorithms. They train the computer by showing it thousands of confirmed examples, teaching it the digital fingerprint of a Roman villa, a Mayan platform, or an ancient irrigation ditch. Once trained, this artificial intelligence can then scan thousands of square miles of fused data, automatically flagging locations that match the patterns. It can perform in minutes a task that would take a team of human experts decades, sifting through the noise to find the subtle signals of lost history. This collaborative approach between human intuition and machine precision is the true cutting edge. It allows us to build reconstructions of the past that are not just visually stunning, but also deeply reliable, grounded in multiple, independent lines of evidence. Yet this flood of digital resurrection also brings a profound new responsibility. With the power to see so much of our shared heritage so clearly, we must now decide how to protect it and who this rediscovered past truly belongs to. This new power to see the unseen carries with it a profound and urgent responsibility. Our most advanced tools for discovery can, in the wrong hands, become the most efficient tools for destruction. The same satellite maps that guide archaeologists to a lost city can just as easily guide looters to its treasure vaults. These treasure hunters are not interested in history, they are interested in profit, and they use our own spectral signatures to pinpoint their targets, digging indiscriminately and destroying the context that gives artifacts their true meaning. This creates a painful dilemma for the scientific community, a constant tug of war between transparency and protection. How much data should be made public to advance global knowledge, and how much must be kept secret to safeguard our collective heritage from being erased forever? But the ethical challenges run even deeper than theft. A discovery from space is never just a discovery, it is an intervention. When a satellite reveals a sacred ancestral site or the ruins of a village on land claimed by an indigenous community, it can ignite complex conflicts over land rights and cultural identity. Whose story is being told and who has the right to tell it? For generations, the knowledge of these places was held in the oral histories and traditions of the people connected to them. A map generated from orbit can feel like a sudden, impersonal claim on a deeply personal past. This is why the true revolution is not just technological, it is collaborative. The most responsible and insightful archaeology now begins not with a satellite pass, but with a conversation. It means working directly with descendant communities, respecting their intimate knowledge of the landscape, and acknowledging their sovereignty over their own heritage. They are not subjects of study, they are essential partners. Their stories provide context that no spectral signature can ever detect, and their guidance ensures that discovery does not become exploitation. The ultimate goal shifts from simply finding a site to understanding and preserving it in a way that honors the living culture it represents. The light from space gives us the map, but it is our shared humanity that must guide the journey. The data streaming down from our satellites is a fire hose of history, far too much for any human mind to drink from. We have mapped entire continents in spectral detail, creating an archive so colossal that manually searching it would take countless lifetimes. This overwhelming volume is the very reason a new partner has entered the archaeological team, artificial intelligence. The process begins with training. Researchers feed a machine learning algorithm thousands of examples, showing it the precise digital fingerprints of known archaeological sites. They teach it to recognize the subtle spectral curve of a buried wall, the unique thermal pattern of an ancient hearth, and the specific shape of a ceremonial platform seen from above. The algorithm is not programmed with rules, it learns from the data, gradually building its own internal model of what the past looks like. Once this education is complete, the AI is set loose. It can scan tens of thousands of square kilometers of satellite imagery in a fraction of the time it would take a human, its digital eyes never tiring, its attention never wavering. It sifts through the endless noise of the landscape, flagging only the pixels that match the patterns it has learned. This is not about replacing archaeologists, it is about empowering them. The AI acts as an impossibly efficient scout, presenting a curated list of the most promising targets for human experts to explore. The results have been staggering. One project in Mesopotamia used this approach to analyze a vast region. The machine learning model identified the spectral signatures of countless ancient mounds, the remains of mud brick settlements that had long since melted back into the earth. It discovered not just a few new sites, but thousands of them. When plotted on a map, these points revealed a breathtaking population density of the ancient world, showing trade networks, agricultural heartlands, and the rise and fall of urban centers on a scale never before possible. This shift is fundamental. We are no longer just finding single sites, we are modeling entire civilizations. We can ask the data profound questions. How did climate change affect settlement patterns across a whole river valley? Where did people move during a period of drought or conflict? This automated prospecting is turning the grand narrative of human history into a quantifiable science, allowing us to test our biggest theories against the cold, hard evidence of the land itself. The future of discovery is not just in the stars above, but in the algorithms that help us decode their light. The Nile Delta has always guarded its secrets well. For centuries, this vast, fertile triangle of land has been a puzzle for archaeologists, its ancient history buried not only by time but by the very river that gave it life. The Nile's branches have shifted dramatically over thousands of years, silting up old channels and carving new ones, while a dense modern population has built cities and farms directly atop the ruins of the old. Finding a specific lost city here was like searching for a single page torn from a book and tossed into a river. The traditional approach of digging test pits was almost hopeless. But spectral imaging offered a way to read the water itself. The key was in the soil. An ancient river channel, even when completely filled in and invisible on the surface, leaves a permanent hydrological ghost. The sediments in a former riverbed are different from the surrounding earth, affecting how the ground holds moisture and retains salts. Using satellites equipped with sensors that detect subtle differences in soil moisture and salinity, researchers began to trace these spectral lines across the delta. They were not looking for stones or bricks, but for the faint, damp impressions of rivers that died millennia ago. Slowly, a forgotten map began to emerge from the data. The spectral signatures revealed the precise paths of lost Nile branches, the very aquatic highways that would have been the lifeblood of ancient trade and settlement. This rediscovered geography was the master key. Any major city or port from the New Kingdom period would have been built on the banks of these waterways. By following the spectral trails of the vanished rivers, archaeologists could predict with stunning accuracy where to find the settlements that depended on them. This method has led to the discovery of several major sites, administrative centers and bustling ports that controlled the flow of goods between Egypt, the Mediterranean, and the Near East. We are now learning that the Delta was far more than just the agricultural heartland of Egypt. It was a dynamic, urbanized hub of international commerce. The light from space is not just finding lost cities, it is rebuilding the entire economic and geographic framework of a civilization, restoring the forgotten landscape that pharaohs and merchants once knew intimately. Our eyes are limited to the surface, but the story continues deep underground. To uncover these hidden layers, archaeology turns to a different kind of light, one with wavelengths so long they can literally pass through the earth. This is the domain of synthetic aperture radar, a technology that gives us a form of X-ray vision from space. Unlike optical sensors that passively collect reflected sunlight, our satellite is an active explorer. It constantly transmits pulses of microwave energy down toward our planet. These are the same type of waves used in a microwave oven, but far less powerful, and they behave completely differently than the light our eyes can see. When these microwave pulses strike the ground, most of them bounce right off the surface and travel back to the satellite. But a portion of them do something almost magical. They penetrate the dry, loose upper layers of soil and sand. The exact depth depends on the aridity and composition of the ground, but in perfect conditions they can probe several meters down. Once beneath the surface, these energy waves interact with anything buried there. A smooth, flat layer of natural sediment will scatter the energy in one way. A buried stone wall, a compacted ancient road, or the interface between different soil layers will reflect the signal back with a distinct pattern. The satellite's sophisticated receiver measures two critical things about the returning signal: its intensity and its phase, which is essentially the precise timing of the wave's return. By analyzing these subtle differences, scientists can detect the ghostly presence of structures hidden far below. This technique has proven revolutionary in the world's driest deserts. In the hyper-arid sands of coastal Peru, SAR has mapped the subsurface traces of ancient roads connecting settlements of the Nazca and Moche cultures, routes that have been completely invisible for over 1,000 years. In the Taklamakan Desert of China, one of the most forbidding places on Earth, radar has detected the outlines of walls and buildings from lost Silk Road outposts, their spectral forms preserved just beneath the shifting dunes. These are environments where optical and thermal methods can be blinded by the uniform surface, but where radar's penetrating gaze excels. The true power, however, emerges from collaboration. A hyperspectral image might reveal the surface chemistry of a site, painting a picture of ancient industry. A LIDAR scan provides the precise topography of the ground itself. When you layer a SAR subsurface map over these other datasets, you are no longer just looking at a flat picture. You are building a three-dimensional model of history from the deepest foundations to the topsoil. You can see how a buried road aligns with a surface track, or how a subterranean wall corresponds to a faint vegetation mark. This non-invasive probing creates a complete understanding of an archaeological site, allowing researchers to plan excavations with surgical precision or to preserve a site entirely by studying it from orbit. We are learning to read the Earth in volumes, not just on surfaces, turning the very soil into a transparent window to the past. This relentless erosion is a race against time, and the finish line is the sea. Climate change is not a future threat for coastal archaeology. It is a present-day emergency, with rising tides and intensifying storms chewing away at shorelines that hold millennia of human history. These are not just piles of old stones being lost. Each site is a unique library, a time capsule filled with irreplaceable information about how our ancestors lived, traded, and adapted. The water is now closing in on these fragile archives, and we are in a desperate sprint to read the last pages before they are dissolved by the waves. Satellite spectral imaging has become our most critical preservation tool in this fight. By continuously monitoring the coasts from space, scientists can track the pace of erosion with startling precision. They can see which cliff faces are receding fastest, which dunes are collapsing, and exactly which archaeological sites have moved from being stable to being critically endangered. This is not a passive observation, it is an active triage system, allowing researchers to prioritize which sites need immediate, on-the-ground attention before they vanish completely. On the windswept coasts of Scotland, this drama is unfolding in real time. Severe storms have clawed away at the turf, suddenly exposing ancient middens, the rubbish heaps of prehistoric communities. To the untrained eye, they might look like simple piles of dark soil and broken shells, but to an archaeologist, they are a detailed ledger of daily life. The bones within tell us which animals were hunted or herded. The shells reveal changing sea temperatures and marine ecosystems. The fragments of pottery and tools speak to trade and technology. These newly revealed treasures are incredibly vulnerable, often washing away in the very next storm. Here, spectral sensors provide a rapid response. They can be tasked to fly over the exposed site, capturing the detailed chemical and mineral composition of the midden in a single pass. This creates a permanent digital record of the site's composition, a dataset that can be studied for generations long after the physical evidence is gone. This application of the technology carries a different weight. It is not driven by the thrill of finding a lost city, but by the solemn duty of saving a memory. We are using the most advanced eyes in history to conduct a dignified, digital funeral for the countless coastal sites we can no longer physically protect, ensuring that their stories do not disappear with the land that holds them. The ocean floor holds drowned continents of human history, landscapes lost when the glaciers melted and the seas rose. These vast continental shelves, now submerged under shallow coastal waters, were once the fertile plains and river valleys where our ancestors lived and migrated. Finding their traces on the seabed has always been a monumental challenge, but the same spectral light that reads the land is now learning to see through water. While water absorbs and scatters light, sophisticated algorithms can now account for this distortion, peeling back the liquid veil to reveal the spectral fingerprints of the world beneath the waves. In the clear, sunlit waters of the Mediterranean, for example, the distinct spectral signature of ballast stone from a Roman merchant ship stands out sharply against the uniform sand of the seabed. The dense, specific minerals in those stones reflect light in a way that the surrounding environment simply does not, creating a clear target for a hyperspectral sensor. This is not just about finding shipwrecks, it is about mapping entire submerged landscapes, the building materials of a sunken settlement, perhaps limestone blocks or fired clay bricks, possess a unique chemical identity that persists for millennia. Even when covered by a thin layer of sediment or seagrass, their spectral signal can be isolated from the organic matter and sand around them. This breakthrough is birthing an entirely new discipline, maritime spectral archaeology. It allows for the systematic, non-invasive survey of thousands of square miles of coastal waters, searching for the ghostly outlines of river channels, hearth sites, and tool-making workshops that have been drowned for over 10,000 years. We are no longer just skimming the surface of the ocean's mysteries. We are beginning to chart the lost geography of the continental shelves, the very coastlines that the first explorers of the Americas and Australia would have followed, creating a map of the human journey across a world that vanished beneath the rising tides. The hunt for history is no longer confined to the budgets of national space agencies. A quiet revolution in the business of space itself is fueling this archaeological gold rush, with private companies launching constellations of small, powerful satellites that orbit our planet. Firms like Planet Labs and Maxar Technologies operate fleets of these nimble eyes in the sky, providing a constant, unprecedented flow of high-resolution imagery from virtually every corner of the globe. This commercial model has fundamentally changed the game. In the past, an archaeologist might have waited months or even years for a government satellite to pass over their site of interest, often at a less than ideal time. Now they can directly task a commercial satellite, commissioning it to fly over a specific patch of desert or jungle at the perfect moment. They can request a pass right after the harvest, when the stubble of crops reveals hidden patterns in the soil, or at the precise low-sun angle of a winter morning, when shadows cast by subtle ruins grow long and distinct. This shift from requesting data to commanding it has broken open a world once reserved for a select few with the right connections. The cost of accessing this incredible resource has plummeted, empowering small university teams, independent researchers, and even dedicated citizen scientists to join the search. A historian in a campus office can now scan an entire province for Roman roads, while an enthusiast can analyze satellite data of the English countryside from their home computer, looking for the spectral ghosts of medieval villages. The marketplace has become an unexpected yet powerful engine of discovery, turning the spectral hunt for the past into a truly democratic, global endeavor. This newfound access is not just about taking pictures, it is about orchestrating the light itself to ask the most revealing questions of the land. A single Roman pot sitting in a museum case holds secrets invisible to the naked eye. Where was its clay dug from? What journey did it take across the ancient world? And what does its composition tell us about the people who made it? The same science that reads landscapes from space can now read these individual artifacts, turning each one into a detailed passport of its own history. This is the power of spectroscopy in the laboratory, a direct application of the same principle that guides our satellites. Techniques like X-ray fluorescence and Raman spectroscopy work by probing an object with a specific type of light. In X-ray fluorescence, a handheld device bathes the artifact in harmless, low-energy X-rays. This causes the atoms in the object to become momentarily excited, and as they calm down, they emit their own unique secondary X-rays. Each chemical element, from iron to copper to lead, emits a signature pattern of energy, a precise spectral fingerprint that the device reads. Raman spectroscopy works differently, shining a laser onto a tiny spot, perhaps on a faded painted surface. The laser light causes the molecules in the pigment to vibrate, and the way they scatter the light back reveals their exact molecular identity. The beauty of both methods is their complete non-invasiveness. We can learn the elemental recipe of a bronze dagger or the precise mineral used for the blue in a medieval manuscript without ever scratching its surface. This analytical power solves long-standing mysteries of provenance. For centuries, archaeologists might have guessed that a particular style of pottery originated in one region. Now, by comparing its spectral signature to a vast library of clay samples from known ancient quarries and workshops, they can say with scientific certainty, this clay came from that specific hillside in Cyprus, or this glaze matches the unique mineral impurities of a riverbed in Anatolia. A single pot becomes a data point that traces a trade route across the Mediterranean. This ground truthing is the essential link that completes the cycle of discovery. When a satellite spectral image suggests there was a pottery production center in a certain valley, scientists can send a team to that exact location to collect clay samples. Back in the lab, they analyze those samples and add their spectral signatures to the library. Then, when they find a pot of unknown origin elsewhere in the world, they can check its signature against the library. A match does not just confirm the pot's origin, it powerfully validates the original satellite data. The macro view from orbit and the micro view from the lab enter a continuous dialogue, each making the other smarter and more accurate. The story of a civilization is written in both its grand landscapes and its humblest objects, and light provides the universal language to read them both. This same technology that finds lost cities is now putting a trowel in the hand of anyone with an internet connection. Archaeologist Sarah Parcak, a pioneer in satellite archaeology, took this principle and built a global movement with it. Her platform, Global Explorer, is a brilliant piece of digital citizen science. It invites people everywhere to become virtual surveyors, scanning thousands of satellite images from their own homes to search for the telltale signs of looting pits or the subtle spectral hints of a buried structure. This is armchair archaeology on a planetary scale, transforming the hunt for history into a collaborative game where a teacher in Tokyo or a student in Brazil can make a genuine discovery that protects our shared past. The engagement does not stop there. The breathtaking visualizations created from spectral and LIDAR data are revolutionizing how we experience history outside of academic journals. Walk into a modern museum, and you are no longer just looking at a fragment of a wall. You can stand before a massive screen and watch as a three-dimensional model of an entire Mayan city rises from the digital terrain, its plazas and pyramids reconstructed with stunning accuracy based on the subsurface data. Documentaries now use these fly-through animations not as speculation, but as scientific illustration, taking viewers on a journey through a perfectly mapped ancient landscape. This visual power makes the abstract tangible and the inaccessible immediate. It bridges the immense gap between a complex scientific paper and the public's innate curiosity about where we come from. By making the invisible brilliantly visible, this technology does more than just advance research. It builds a global constituency for cultural heritage. It fosters a deep, personal appreciation in millions of people, creating a world that is more invested in understanding and protecting the fragile pages of our human story. The search for the past is no longer a solitary pursuit in a dusty trench, but a collaborative, worldwide endeavor fueled by shared wonder. The resolution of our spectral eyes is about to become impossibly sharp. We are on the cusp of a new generation of sensors, missions designed not just to see the past, but to watch it with a clarity that borders on the cinematic. The next wave of satellites will capture the Earth in hyperspectral video, recording not a single moment in time, but a continuous flow of spectral information. Imagine being able to observe an entire landscape change over the course of a day, watching how the thermal signatures of buried structures evolve from dawn to dusk, or tracking how moisture moves through the soil of an ancient field after a rainstorm. This dynamic view would reveal processes and patterns that are completely invisible in a static snapshot, turning a single portrait of the past into a full-length documentary of the land itself. Alongside these powerful new eyes in the sky, a fleet of specialized sentinels is being planned. Entire constellations of small, agile satellites could be dedicated solely to the guardianship of cultural heritage. These nimble orbiters would provide constant, real-time monitoring of the world's most vulnerable archaeological sites, automatically alerting authorities to new looting scars, the encroachment of construction, or the erosive impact of a severe storm. This would transform heritage protection from a reactive effort into a proactive, planetary-scale immune system. But the true frontier lies in the fusion of all this data into a new kind of reality. Picture a field archaeologist holding a tablet over a seemingly empty meadow. Through its screen, powered by augmented reality, the spectral ghost of a Roman villa superimposes itself perfectly onto the landscape. They see its walls rise from the earth, its courtyard materialize at their feet, all built from the precise LIDAR and hyperspectral maps created from orbit. This data can then be merged with ground-penetrating radar scans from drones, revealing the subterranean foundations, and layered with decades of excavation records and artifact finds. The ultimate expression of this is a complete digital twin, a virtual reality reconstruction of an ancient city so accurate and rich with data that a researcher can literally walk its streets, experiencing not just an artist's rendering, but a scientifically rigorous model of the past. The revolution that began with learning to decode light is now accelerating into a future where the boundaries between the digital and the historical, the orbital and the intimate, will blur into irrelevance. We are building a time machine not of metal and gears but of data and light, and we are only just beginning to learn how